In this video, we'll be talking about the Candela, which is the SI base unit of luminous intensity. The Candela is actually a Latin word which means candle, Candela, Latin word for candle, and it is the luminous power per unit solid angle emitted by a point light source in a particular direction. So the candela is actually the measure of light perceived by the human visual system. Candela is the only SI unit that is based on human perception, and that perception is vision, and it doesn't relate to the light shining from an object, or it doesn't relate to the electromagnetic radiation that our eyes cannot detect or see, like for example radio waves or x-rays. So a common candle emits about roughly 1 candela of luminous intensity. So we're gonna go back through some of its short history in before 1948. So before 1948, some countries had various standards for measuring luminous intensity, but they was just based on a standard candle, which were so a candle can vary from many things, from the wax, from the type of wax that was used in the candle to the filament that was used in the candle. So at that time, one of the well-known standard was the English standard of candle power, which was the candle power, which was candle power. So as I just mentioned, let me just draw a rough image of a candle. So a candle can vary. So the standard that was used back in the days was varied differently, depending on the size of the candle, depending on the filament that was used in the candle, and the type of wax that was used for the candle. So at that time, the well-known standard was the English standard, which was the candle power. So, what is the candle power? Well, one candle power was the light produced by a pure spermaceti candle that weighed about 76 grams and burned at the rate of 120 grains per hour. 120 grains equal to 7.8 grams per hour. So, the spermaceti is a waxy substance that was found in the head of a sperm whale. So, what was the English standard for candle power? Okay, the candle power was spermaceti candle, whose weight was around 76 grams, and that burned about 120 grains per hour. I'm not gonna write 120 grains, instead I'm just gonna write 7.8 grams per hour. So spermaceti the is a candle that was made from the waxy substance that was found in the head of a sperm whale. So because the standard varied, as I told you in just now, that the standard varied from the size of the candle, from the filament, from the wax, different type of wax used. It was very clear that a new definition was needed for the standard, for a candle standard. So in 1876, just gonna, where do I write? I think I'm gonna just write down about here. In 1876. In 1876, oh, looks like I made a mistake. Not in 1876, but in 1879. In 1879, Jules Violet proposed a standard based on the light emitted by 1 centimeter square of platinum at its melting point, called as violet. The light emission was due to the Planck radiator black body effect. So who is this person? This is the person. This is the person. Just gonna put it him here. So this is the person, Jules Violet, who proposed a new standard. So what was the standard? By melting by melting the platinum, by the platinum, and the light emitted by melting the platinum due to the black body effect. And just gonna write it down. Light emitted by, let me just write the name here again, Jules Violet. Light emitted by 1 centimeter square of platinum at its melting point, which is about 1768 degrees Celsius. So this light emission was due to the black body effect. We're gonna talk about it in the future lectures in a brief detail about black body. But basically, what is a black body? A black body is a body that absorbs any type of radiation. It is also a perfect it is also a perfect emitter of radiation, plus it's a perfect absorber of radiation too. So this is the black body. So we're gonna talk about it briefly in the future videos, but just for the sake of this video, a simple concept is this: black body is an excellent absorber. It absorbs every wavelength of radiation, and it also at the same time it's a perfect emitter of radiation. But as we know that in the real world there's no such thing as perfect emitter or radiator, but this is just a uh, there's no such thing as a perfect emitter of radiation, but there are some bodies that are closer to perfection, not perfect, but closer to perfection. So now the International Committee on Illumination and the International Committee on Weights and Measures proposed a new candle. The legislation was put in effect in 1948 by the International Committee on Weights and Measures. So the new value of candle that was proposed by the International Committee on Weights and Measures and International Commission on Illumination, they they chose the value of, similar to the previous unit candle power by dividing Violet by 60. So where do I write? Hmm, just gonna write new candle here, or actually just right beside it, new candle. So what was a new candle? The new candle, the definition was the value of the new candle is such that the brightness of the full radiator at the temperature of solidification of platinum, basically this temperature 1768 degrees Celsius of platinum is 60 new candles per square centimeter. So just gonna write it down. The the value of the new candle, the new candle is such that the brightness of the full radiator at the temperature of platinum of solidification of platinum is 60 new candles per square centimeter. So the 60 new candles per square centimeter is because they wanted the definition similar to the previous unit, which was the candle power. So that is why they chose this 60 new candles per square centimeter. They actually wanted to make it similar to the previous unit candle power by dividing the viole with this was called 1 viole actually, divided by 60, hence the definition of new candle. And then in 1948 the new candle unit was renamed Candela by the ninth General Conference on Weights and Measures in 19 in 1948. The new candle the new candle was renamed to Candela by 11th by the by the ninth General Conference. Just gonna write CGPM, which stands for the General Conference on Weights and Measures. In 1948 they just renamed it to Candela, and then 1967 in 1967 the 13th General Conference and Weights and Measures removed the new candle term that was used in the definition and gave a more accurate definition of the candela by specifying atmospheric pressure to the freezing platinum. So the whole thing in 1967, what the 13th General Conference on Weights and Measures did was that they removed this new candles They removed this new candle definition, the new candle that was used in the definition, and they gave it more specifying detail by by specifying atmospheric pressure to the freezing platinum. So what was the definition then? The definition was: the candela is the luminous intensity in the perpendicular direction of a surface of 1 by 600,000 square meter of a black body at the temperature of freezing platinum under a pressure of 101,325 newtons per square meter. So let me just write it down. Just will take some time. So the candela is the luminous intensity in the perpendicular direction of a surface of 1 by 600,000 square meter of a black body at the temperature of freezing platinum at the temperature of freezing platinum under a pressure of 101,325 newtons per square meter. So this was the definition. The only thing that really changed was specifying atmospheric pressure to the new definition. So I think this definition is a big one. So I'm just gonna resize the definition. Okay, resize, and this is perfect. Okay, now in 1979, in 1979, just gonna draw down in 1979. In 1979, because of the difficulties of Planck radiator meaning black body effect at high temperatures, and with the advances in radiometry. Radiometry is actually measurement of optical radiation. Radiometry, radiometry, measurement of optical radiation. Optical radiation. Because of the difficulties of the Planck radiator, the black body effect at high temperature. Why at high temperature? Because as we know, black body is also in a field, is in the quantum realm. So in quantum realm there are always some kinds of uncertainties. So when we are talking about us are defining a unit which were trying to basically end every uncertainty possible. So when it comes to quantum, there's all sorts of uncertainties. So instead of going to that effect, to the black body effect, for trying to measure the unit of Candela, There was another field who made major advances, and with what was that field? It was the radiometry, which is the measurement of optical radiation. And because of that, because of these difficulties and the advancement of radiometry, the 16th General Conference on Weights and Measures, the 16th CGPM, the General Conference on Weights and Measures, adopted a new definition for Candela. So what was the definition of Candela? Just write it down again. So the definition was such as follows: the candela is the luminous intensity in a given direction of a source that emits monochromatic radiation. Uh, let's highlight this word here. Highlight with orange color. Emits monochromatic radiation. So, what is monochromatic radiation? The monochromatic radiation is the radiation that has a constant frequency. For example, which has a constant frequency. The frequency doesn't change. So it has only one specific color. So, what was the frequency chosen? The frequency chosen was of frequency 540 multiplied by 10 power 12 hertz. So this was the monochromatic radiation, which was of the frequency 540 multiplied by 10 power 12 hertz, and it does not change. It is the constant frequency. That's why it's called monochromatic radiation. Our radiation whose frequency doesn't change, it always remains constant, and that has radiant intensity in that direction of 1 by 683 watt per steradian. So watt per steradian. The steradian also is a unit, but it's a dimensionless unit, it's a geometrical unit. So after I'm done with the last SI unit, which will be the mole, I'm gonna go in detail topic with with the geometrical, with the supplementary units. These are just basically unitless dimension units. Uh, Basically, supplementary units are doesn't have a unit because they are purely geometrical quantities. The steradian, how do I put it in simple terms? In simple terms, for example, let's consider a radian. What is one radian? Radian is actually one dimensional. For example, a simple section of it will be one radiation of one sorry radiation of one radian. So this will be of 2D. 2D meaning circle. Basically, one radian is just a section of a 2D circle. So what is the radian? Just in simple terms, I'm explaining this in the next coming videos. I will go in more detail. So what is steradian? Steradian becomes a section of, instead of a circle, it becomes a sphere. Steradian is actually 3D, which is actually a sphere. So it is a section of a sphere. So what is actually a section of a sphere? It sort of shapes like a cone here. So it kind of is a cone shape. It actually a cone shaped section of a sphere, which is the steradian. Radian is 2D, steradian is 3D. Radian is a section of a circle, while steradian is a section of a sphere, a 3D, which shapes like a cone. So I hope you get it. Next, the new definition did not rely on platinum. So this definition, as you can see, it didn't rely on platinum in any way. It relied on a monochromatic radiation. It defined a specific one particular frequency of light, which was 540 multiplied by 10 power 12 hertz. So this frequency of light, it actually has a greenish yellow type of color. Let me write it. So this frequency has greenish yellow color. So this color, why choose this color? Because this color is actually most sensitive color in the daytime. In daytime, this greenish yellow color is the most sensitive color with respect to our eyes, with respect to our visual system. As I said it in the starting of the video, that this unit is based on human perception of vision. So according to because of the of considering human perception of vision, our eyes are more sensitive to greenish yellow color in the daytime, and in the nighttime blue is the most sensitive color to our eyes. So, and after 1 by, what is 1 by 683 watt per steradian? Watt per steradian, get rid of that for a second. Why chose 1 by 683? So 1 by 683 was chosen so that a new definition would match with the previous definition. That is why the 1 by 683 was chosen, because it should be matched with the previous definitions. And then in 2018, the 26th General Conference on Weights and Measures, I redefined the candela again. Mm, just resize this whole explanation, and then we're gonna move on to the last, which is the current sorry, the current definition. Resize. Okay, perfect. Let's go to the last definition, which is now the definition. In 2016, the 26th Conference on Weights and Measures, the 26th General Conference on Weights and Measures, which is CGPM, redefined the candela. What was the definition? Then the candela is defined by taking fixed numerical value. Oh, just before saying the definition, remember, with the last videos of the SI base unit, what I told you about, that the SI base units are now tied to the universal constant, to the natural constants of the universe. So this is basically happened here. They made a constant for it, but that constant was based on the human perception, on the human visual system. This was the constant. So the definition was based on that. Just gonna write the definition first. The candela is defined. Candela is defined by taking fixed numerical value of the luminous efficiency efficacy of monochromatic radiation of frequency the same frequency 540 multiplied by 10 power 12 hertz, and then which is kcd. Kcd actually that constant to be, so this is the constant which is 683 when expressed in the unit lm, which is for lumen. Lumen is the amount of visible light emitted by the source, by visible light emitted by the source per unit of time. Just let me finish this whole definition, write the whole definition down, and then we're gonna talk in detail later. Or what, which is equal to ct, which is candela. SR is for steradian per watt, or CD candela steradian per kilogram per meter square second cube, where the kilogram, meter, and second are defined in terms of H, C, and delta VCS. Oh, the V is actually written as, this is how it's written, delta VCS. Okay, the candela, really sorry about my terrible handwriting. The candela is defined by taking fixed numerical value of the luminous efficacy. So here the luminous efficacy is this luminous efficacy. What is luminous efficacy? The luminous efficacy is the total amount of visible light that the source produces with a certain amount of power. The total light, visible light, actually, the visible light produced by the source with a specific amount of power, with a certain amount of power of monochromatic, the radiation with the constant frequency, which is the which what is the constant frequency, 540 multiplied by 10 to power 12 hertz, which is the greenish yellow color that is more sensitive to human eyes in the daytime. Luminous efficiency of monochromatic radiation of frequency 540 multiplied by 10 to power 12 hertz, kcd, to be 683 when expressed in the unit lumen per watt. Lumen here, lumen is the amount of visible light Lumen is the amount of visible light emitted by the source per unit of time per watt, which is equal to CD, which is equal to Candela steradian. So lumen, when we broke it down to its basic units, is Candela steradian. Candela steradian, as I said, per unit of time, but it's also considered with the steradian, the 3D, the cone-shaped section of a 3D sphere, candela steradian per watt, or candela steradian per kilogram per meter square second cube. So here the per watt was basically broken down into their basic units, to their basic units, which is the per kilogram meter per kilogram per meter square second cube, where the kilogram, meter, and second are defined in terms of HC and delta BCS. So these last two lines are saying that kilogram, meter, and second are based on these three constants. H is the Planck constant, which is for kilogram, which was used to define the new value, the new definition of kilogram. C was used to define the meter, and delta VCS is the frequency of the cesium-133 atom for defining the second here. So the KCD here, the KCD actually the main thing here, because as to the previous videos, the base units are now tied with the constant, with the natural constants of the universe, and KCD is no exception. And this candela is no exception. We also tied it to our natural constant, but it was based on the human vision perception. So this is the thing that helps us to define the candela. The value of KCD is 683 lumen per watt, as given here, 683, and its units are lumen per watt. So watt was broken down into kg meter square per second cube. So how does it work? how doesn't it, how does it work? Sorry. uh, Watt is actually the unit of power. Let me just explain. P for power, and then what is power? The work done in time. So broke down work into FT. Gonna break down time, T minus 1. F is actually ma dot d dot t. So break it down again. First of all, just resize this whole big value here, not the value definition, I'm sorry. Just resize it first. Okay, resized it. Now, where do I? Okay, then here, then. Okay, then we have m. M is for mass, kilogram, basic the unit of it. Acceleration is actually, when we break it down even further, acceleration is v by t. We break it down further, it becomes mt squared by d. D is for distance, which is for meter. M is meter also here. The m was here, m was the for mass, and was changed to the kilogram. And then we have t minus 1, also breaking it down into its basic unit, which is the second. Kg, we have kg meter square by and second s minus 3. So this is for watt, which is power. And here we have the reverse values here, because obviously the watt was written as, this is for watt, and for this value, for this here, For here, it was for per watt. That is why the values, the powers are changed here, are flipped out. So I think that's it for today. I think I have covered it all. Yep, this is the whole lecture for Candela, the unit of luminous intensity. It it's only, remember, every seven, the seven base units are, of all the seven base units, this is the only unit that is based on human vision perception. And Candela, the definition was changed, was again rechanged, was changed, was redefined in 2018. Well, basically 1979 and 2018, there only the main difference was of the natural of the universal constant, but that was put in this in the 1970s, in 1979 definition, and nothing else. So yeah, I hope you have liked this video, and I'll see you guys in the next video then. Next video we'll be talking about the mole, which will be the our final SI base unit, and after that, well, I'm gonna go with the supplementary units, the geometrical units. So please like this video, subscribe to my channel, and share this video to everyone. And I'll see you guys in the next video. Thank you.